Well, welcome everyone. It's very exciting to be here at JuliaCon in person after a couple of years without actually seeing the people live. And yeah, so the workshop about differentiable modeling on GPUs. We set that together with my colleague Sam Omlin he's working at the Swiss National Supercomputing Center, and we're long-term collaboration in GPU computing for earth and environmental sciences in the application range. And with Ivan, who didn't make it in person for geopolitical reason, which is really annoying. But yeah, hopefully we could make it that he support us and will present part of the workshop remotely. So well, hi Ivan, and thanks for being around, even if it's not in person.
Hi everyone.
And yeah, well, so as I said, I just updated the JuliaCon on the program, so the workshop description. Now there is a GitHub link, and so the setup today will be that basically all what we'll do is contained on this JuliaCon 23 GPU workshop repository, and so the entire content is in the README, and the codes and scripts and all what you need is also there. So I will kind of do some little intro, and we'll go through that README basically in the next 3 hours. I'll start. Ivan will do the second part. I'll do the first part. And I guess Sam may jump in for some technical details, but I guess he mostly will also just be here to go around. If you have questions, feel free to raise your hand. Don't be shy. And yeah, if you have questions, feel free also to ask questions. We have a couple of mics that so everyone can hear. And yeah, well, I guess there are no stupid questions. I'm definitely not the most knowledgeable in the room, neither for numerics or whatever thing. I'm just kind of enthusiastic to share our latest development with you. So yeah, just kind of feel free to interact. Yeah, well, I guess that's it. So I hope it's okay, but I'll switch screens. So most likely I will be on the README for when we explain things, and then I'll do the coding on my VS Code setup here, where I'm connected to my remote GPU server. I hope the size is okay. If anything, just let me know, if it's kind of too big, too small, let me know straight. That not kind of wait the end to say, oh, by the way, it would have been great to have I don't know, different font size. Yeah, well, I guess that's it. So is there any urgent question before we dive in? Well, if not, then I guess we can start. So I populated, there is a small print that you can read. So today, I guess, well, the goal is that we will take a PDE, a partial differential equation that's pretty common. So it's kind of a diffusion-like equation. And, well, it's a bit on the vanilla side because, well, it's only 3 hours. And, well, I guess we all have very different backgrounds. But still, I mean, I still try to wrap it in something that could sound that's actually not that far from current things that's done in geoengineering maybe. So these kind of geothermal operations. So when you have a reservoir in the subsurface, so well, I'm kind of geologist by training. So well, there's what we see, then there is the underground, and the underground, well, it's kind of rocks, and rocks have holes, and they're filled with fluids. And well, one of the thing one can do is try to use it as heat storage extractor. So one wants to pump in fluids and extract fluids on the other side. And well, here try to take a mathematical model that would explain this based on physics and try to numerically solve it, basically. So that's the first step. And then, then at some point, we're happy with that forward solutions, so kind of a predictive model. If I can control my injection extraction rate, then I can predict how the fluid flow is in the subsurface, given that I know the structure of the subsurface. And there, like, the things become interesting, because usually I don't know the structure of the subsurface. So I would be interested in more an optimization-like problem where I actually can I retrieve somehow those things that I don't see in what's called inversion-like things, which is pretty common in, for example, geophysics. And so we'll do it in a, let's say, alternative way, maybe than most of you know, using like simple tools, maybe very classical approach, but combining this with like new things. And there it's really where why we do it here at JuliaCon is that we'll actually use help from automatic differentiation, and that's kind of up to now really mostly only possible in Julia, because, well, since Julia is mostly written in Julia, like the whole stack is differentiable. And, well, thanks to great work by, all the people who maintain this AD stack and Julia GPU that I want to acknowledge here as well. Well, this is really possible, and I guess that's pretty new. And the idea, the whole thing will do, so the approach is kind of the design behind, or the idea is that we do things in a way, ideally, that is scalable, which means, like, well, that because we try to do it on GPUs, we need to rethink a bit how we do it. And then since we do it in a scalable way, then we could push it further and say, well, why not to do it on multiple GPU? Why not to do it on a supercomputer? And so the idea behind, like, usually there is not only one single recipe to make something, like, but the recipe we choose here is with having in mind that these scripts, they could be transferred from 2D to 3D very easily, and then in 3D they could be run like not on one GPU but on 1,000 GPUs on a supercomputer. And yeah, that's a bit the motivation behind, and also that would guide the choice of the things how we do the things. And also we'll try to, we won't use any, we won't use any crazy black box, let's call them packages. So I use some building block packages and some helper packages, but we'll really try to do things, let's say, on our own, such that it kind of maybe demystifies a bit the thing. But like as usual, when I see what I do, I can also track down performance. I can understand what goes wrong and what goes right. And so that's also one thing. And yeah, maybe as a cool feature as well is that even the final code we'll look at, which is like a full code that does like synthetics, inversion, gradient descent on multiple GPU, this code, if I remove just the lines that are due to plotting, it's only 280 Julia lines. So, and that's it. That would scale on I don't know, largest supercomputer or whatever. So yeah, so that's it. And today we won't focus on performance per se because, well, we don't have time to do anything. But yeah, so the approach we do is to target scalability and performance on distributed system and GPU systems mostly. And so, well, if you're interested in that topic, I can recommend a talk that Sam will give later on at the JuliaCon, where we really kind of demonstrate like performance metrics, etc. But for today, we just, you could believe us that the thing works fine. And yeah, if you want to be sure, then you can attend the talk. Yeah, well, I guess that's it. So the scripts are in the script folder, and if you're kind of want to jump straight to some solutions or have a cheat sheet, then there's like the script solution folder where you can find like the corresponding scripts. So, well, yeah, I encourage you to get started. So, well, if you put up Julia and internet, clone the repo, activate instantiate, and then if you run that script, you should be able to get some figure. So I'll just quickly do it on my side just to make sure that that everything is there. Maybe I can just quickly go through the script. So the scripts will look today, they're incremental. So anything I show in the first script, I won't repeat it in the next script because it's basically only adding things so that you're not confused. So, well, if you make a diff, you can, well, anything, nothing changed. So if the visualization is set up here, and then the next script, they just add stuff. But this we can, yeah, you don't have to think anymore like, if you understood it or didn't get it, don't worry, you won't, either you will still understand it until the end or still not get it until the end because we won't change it. Yeah, so what we do here, I just define some helper functions, and then in the main body of my application, I just prepared like some setup that I will explain later, but the way the code will be structured is I have a physics section, which is all about like the physical input, then a numeric section, which is all about like how I discretize my physics on like in a discrete world in my computer, and we're gonna use like low order finite difference on a regular Cartesian staggered grid. It's conservative, it's kind of lightweight, and there are like many things why this is a good approach. And yeah, that's it. So yeah. Then, well, some initialization of a couple of arrays, and then like the Maki machinery to set up a figure and to be able to update it later. So if I run this, can just make sure that my setup is working correctly as well. And yeah, that's it. So I can also recommend that you try to do it on your side. And well, while it's trying to get time to first plot, let me go back to that part. Yeah, so here we are. Try to set it up like this. So we have the code, the command with the REPL, and the figure. So yeah, what we'll see here, that's kind of the fluid pressure pane here. That's the subsurface permeability or diffusion coefficient. That's our fluxes from our diffusion process, and there will be always some convergence information. And here you can see the two little dots. It's like where I have already set up like my two wells, and those will like injection well, extraction well, and some interesting feature like a low permeability barrier. So something that would prevent my flow to go through on that region. So that would be the subsurface structure. I'll come back to that a bit later. So maybe while you're finishing the setup, a couple of words. So kind of why actually using Julia for HPC, what we're trying to do, and that we'll try to motivate in this workshop is that, well, Julia is pretty fast because it's kind of, as you know, compiled just ahead of time, just in time. And it's also, so it's kind of, well, compiled code performance, optimization, and all what goes with, but it's also interactive and high level, so easy to debug, like nice to handle with plotting, etc. So while combining both sounds like it's a good language to do well R&D in scientific computing. But it's also more, so it runs like, it has this good GPU stack support with kind of this native compilation capabilities and other things. So today we'll really use that and motivate the fact that we can use graphic cards, and while we'll also see some lightweight iterative scheme that allows us to do things the way we want, and then use some very cool new features, which is automatic differentiation. And so for our inversion script or scheme, instead of deriving the, what's needed to make an adjoint-based inversion, like it's a classical thing, but the new thing is that we kind of will not do it by hand, but we'll use AD to give us back like the vector Jacobian product directly on the GPU and use that in our iterative scheme to actually like just slightly modify our forward solver to get an adjoint solver for free in that sense. And having short script, so the context that the script should fit into the screen of the computer still holds. So kind of why to bother with GPU computing? It's kind of around for a while. It has, although like CPUs become fatter and fatter, it still has like at least an order of magnitude better performance for our needs, which means like, as you will see, we care about memory bandwidth, and memory bandwidth of GPUs are still about an order of magnitude at least larger than CPUs, and that's really what limits performance in codes that are memory bound like ours. And well, GPUs are everywhere, especially in the supercomputers. So if we reach exascale today, it's just because that machine is full of GPUs. So yeah, why not to use them? Just a brief flight. It's high level. It doesn't meant at like teaching computer scientists in the room about their own topic. I guess it's just more here for consistency and to have like common ground. So performance is kind of a very, well, one could speak a lot about it and different, like go very deep into some things, but on a high level, it's just important to know a bit what are the bottlenecks and what we care about, and then yeah, for sure, we can dive into the rest. But so what we want to see is basically the two things that we care is like the memory bandwidth and a floating point, like the arithmetic performance or memory performance, and which one limits us. That's the two main thing. And well, it's not a secret. We're limited by memory bandwidth in the way we do the thing, but we can quickly check why. So I just pulled up like specs of like, for example, this NVIDIA A100 GPU and like a fairly recent decent AMD CPU. We see that well, the flops to byte ratio in double precision is about like 50 to 60. So basically what says we can, there is a factor 50 in like, we can do 50 floating point operation in double precision for free with respect to the memory transfers. So we are like, the hardware is in that sense memory bound, and our codes are also memory bound because usually solving PDEs, it's kind of, we need to shuffle around more numbers than we actually do operations with them, unless we do like really recursive type of algorithms that would just work on the same type of numbers. And well, at least on the hardware, the reason is just like we have more and more cores on a chip, but like the bandwidth, like the memory pipe doesn't increase like at the same rate. The width of the memory access kind of lags behind, so there is a gap that grows obviously over time. And yeah, well, so the kind of on the numerical limitation, like if we look at the finite difference and well, finite elements and other higher order schemes would be even kind of worse in that sense. So here, just the simple thing, which is like making a finite difference derivative, which is like reading stencil like two neighbors, multiplying by some diffusion coefficient here to compute the flux, dividing by a scalar, assigning this back to our flux is for that simple operation, it's already about 16 byte transferred and only 3 floating point operations. Yeah, so this imbalance plus the machine imbalance makes that we're kind of heavily memory bound. So long story short, what we really need to care is just to monitor that we're efficiently using the memory bandwidth we're having, and that we can, well, put as low pressure as possible on that memory bandwidth, and also have useful throughput somehow. So again, the really cool thing about the GPU is we can optimize code for CPU or GPU, but on GPU, since we're memory bounded and it has higher memory bandwidth, performance will be better. So it's a pretty simple story. And that's what we try to leverage here. And well, to just demo it, we have this, we can look at on the NVIDIA A100, which has roughly 1.4 terabyte second memory bandwidth, how much we can get solving like diffusion step in 2D on that GPU. And that code would be this perf test code that's in the repo. So what's done there, it uses this ParallelStencil, this package that we'll use today, to allow for math close, backend agnostic way of writing stencil operations. So we have this diffusion step function, and we read in our quantity C, make the Laplace operator here, so the second derivative in x and y, multiply by diffusion coefficient, time step, and assign a new to the new buffer. And then we just somehow stress test it. So I have a fairly big array or number of grid points here because I want to, well, make sure that I saturate the memory bandwidth of my device. And then I use BLAbs from benchmark tools to get automatic testing, and this would return, will sample my execution and return the minimum execution time. So I can try running this on my A100 GPU and see what I get back. So that will print here. And yeah, ideally, we should get good performance. And well, we recently discovered, and well, it was kind of also more and more now obvious that, well, CUDA and CUDA Julia is really optimized nicely for this A100 architecture on, at least for the NVIDIA GPUs. And well, the optimizations done under the hood are pretty decent that we get like, without doing crazy thing, we should get like fairly decent performance, close to the actually vendor announced memory bandwidth, but peak bandwidth, but actually doing some, so not only copying memory here, but kind of also doing some actual useful physics computation. So it just takes some time because it needs to sample thing on the. Yep.
Maybe take a look at the ParallelStencil package before, and I tried to run it, and I managed to do it good. And I think it uses a multi-GPU domain decomposition thing going on, right? To do model.
Yeah.
Domain, multiple GPUs, each GPU takes stuff out of the domain, right?
Yeah, so that's not direct. So ParallelStencil in that sense is not, it's not, it doesn't handle this. So that's, yeah, so implicit global grid is the other thing that's for the implicit domain decomposition, yeah.
But you can use that too, right?
Yeah, so the idea is that you can use both independently, but they are, so they can be used together, and that's kind of one of the idea. And when you use them together, you can have some features like communication computation overlap when you do halo exchange, for example, and that's kind of embedded then.
I mean, because I work in geophysics, and I wonder how many GPUs, because there are so many GPUs that you can fit in a single motherboard today, right? Normally, for you to use multiple GPUs like 1,000, as you mentioned, you have to have a bunch of nodes, right? And
yeah.
How big of a model do I have to have for me to have a linear scaling between number of GPUs and performance as I increase the number of GPUs to 1,000? Because there is a latency.
Yeah, I guess I see your, so the question is like about the scale, how it scales as function of number of GPUs. So, and I guess, well, there usually, so kind of long story short, it depends how you make the scaling evaluation. And usually with CPU, one does this strong scaling. So one has a problem and one increases the number of cores or computational resources, and one sees when the optimal is. So then it makes the local problem size per core, per CPU become smaller and smaller, and we increase parallelism. and then there is an optimum somewhere. With GPU, it's a bit different because it's much more sensitive. So usually the way, at least the way we do it, and the way I guess it would be ideal is to find the optimal problem size on one GPU. And once you have that, then you do a weak scaling. So you say, okay, if it's fine for my problem, then I use one GPU. But now if I have like a 10 times bigger problem, I would just need to increase tenfold my resources. But still, this would ensure that your local problem size still would run ideally on one GPU, because that's super sensitive. That's actually really a thing. So you get poor, strong scalability on GPUs usually. So that's one thing. Yeah, welcome. Yeah, so here, like running my vanilla diffusion step on A100 in, Julia that uses CUDA under the hood, I get 99% of memcopy. And it runs here at 1.34 terabytes second. Actually doing the work. So how I measure this, I just say, well, to do my diffusion update, I read in C, I read in D, which are my two arrays. Then I do my stencil, but this shouldn't be counted because, well, I cannot count neighbor operation. This should be somehow cached and accessed without too much cache misses, and written back to C2. So I have 3 memory access of an array of size n, x, and y. And if I divide this by the execution time, I get some throughput in gigabyte or terabyte per second, and then I compare these to what's the memory copy only, and so that's how I get this number, which is cool. Which means actually solving physics on the GPU, I get only 1% off from only copying memory. So and here if I would do more operation, for sure, then I would start to deviate from the ideal memory throughput, because, I may do things so that's a way to kind of track how close I am from the ideal, and the ideal, since I'm memory bounded, is memory copy only. So this would penalize me if any operation I do are kind of too not savvy enough on the memory bandwidth. So that's the idea behind performance. But I guess for that specific topic, I can really recommend Samstock, which will go into much more details on this thing. But yeah, so long story short, with this, I guess, we are happy because kind of to recap that first part is the GPU has a huge memory bandwidth and we can actually use it. And that's really the take message here. So coming to today's little challenge. So that's what we're going to look at. So I already spoiled it a bit, showing some figures before and giving explanation. But yeah, so we have geothermal, I casted it as a geothermal operation modeling, where we have a reservoir with a given permeability or fluid flow transmissivity here in gray, and I have a low, that's permeability over fluid viscosity usually, and that's a low permeability barrier, so there is an obstacle to the flow here in yellow. And I have an injection well, an extraction well, and in geothermal, typically one would inject cold water. Water would flow through the hot region here, and then one extracts warm water and use that for making energy. Have a domain size that's non-dimensionalized, so all the things are written here, and it's kind of it's bounded by impermeable rocks, so I have it's kind of a closed model for today's exercise. And it may sound very easy and naive, but actually there are 3 things that are challenging in numerics and solving the physics that kind of would govern what's going on. And so first, we want a steady state, so we'll get an elliptic solver which has no time derivatives. So it's kind of typically one would use implicit type of solver or matrix-based solver, because then I can just get an implicit solve since I have no time stepper. I have a source term that's kind of can be varying in time and space, and then I would start to need to make different steps. And on top of that, I also have spatially varying material parameters. So my diffusion coefficient is not a scalar, it's not a constant. It can be nonlinear, it can be variable in space, potentially time. So for today, we'll have it variable in space. So it's kind of, yeah, it's an array, and it has like a 6 order of magnitude difference so here it's like reference permeability, and in yellow it's like 6 order of magnitude lower permeability, which makes it like practically impermeable. Equations, this Laplace or elliptic diffusion problem, where I have splitted it here up. So I have the diffusive flux here, which is minus the fluid pressure gradient times permeability, which is diffusion coefficient, and then balance of fluxes, and so the mass balance equation, which is balance of fluxes, and source term, and this here equals 0 because I want a steady state. I don't know why it goes, well, sorry, I don't know why it goes to sleep here and not here. Just shout if it gets black. Okay, yeah, it's a bit like connection is unstable and screen is unstable. We'll see how we'll get there. Okay, so yeah, the way, as I told you, the way we do it with finite differences on a staggered grid. So it's conservative. It has various nice features, and also kind of, well, physically it makes sense. So, well, we have our finite difference cells in black, or our finite different grid in black. It's regular, and we have in the cell center the pressure nodes. If we have temperature, it would be temperature there. And then we have the fluxes that are located at the corresponding faces, and it's really like, well, you can see that if it's kind of finite volume thing, so if I make the derivative of the pressure to get my flux, it would also be physically located at the interface, and so on. And this has like nice properties that that we just kind of happy to use. So, long story short, now we want to solve that system, right? And we don't want to solve it on a matrix with a matrix-based solver, because this has a huge memory footprint. It won't scale for many known reasons. So we want actually an iterative scheme and a lightweight iterative scheme. So the most naive thing one can come up with is say, well, I don't have time, but nothing prevents me, or no one prevents me from, well, putting it back. So what I do here, I replace the 0 from the mass balance equation. I can just put back a time derivative for fluid pressure, or here I call it a pseudo time derivative, because I don't care about time. I want a steady state, but I want somehow a time marching procedure to reach my steady state. And yeah, then I can write down the residual, which is, well, I have my flux, then my flux balance, my mass balance equation, I can like relate it to my residual, and then I kind of can update or try to minimize that residual in an iterative fashion in a very like naive way, and kind of wait, like iterate on this until my residual, here L infinite norm of my residual would go below a given tolerance, and what this is, well, if I choose the tau, my time step, like if I have a CFL condition, so if I make sure that I get this good stability condition there, then it's a, well, robust scheme that would kind of work for whatever, but it's far too slow, right? So it's kind of explicit diffusion, and if I want to reach a steady state, well, we can just check. You can check as well. The code is there. So we can have a look. It's this code, geothermal 2D, no ACK for no acceleration, because later we'll just accelerate that script with some algorithmic technique. So yeah, the code is here. So again, same, like everything that was visualization and we saw in the visualization script stays. Added a couple of things. So now we have a CFL condition. For diffusion, it's 1/4, just to be safe side, 1/4.1. Put a tolerance, so that's my, like until which level I want to converge my problem, basically. Maximum number of iteration I allow, sparsity of checking. So global operation, they're slow, especially when you go on distributed system or parallel system. So you don't want to make max, means, and these things all the time, because you need to, if it's parallel, everyone needs to wait until you gather global information, as we'll see later as well. And the most important thing is just the physics. So we added an iteration loop here, where I compute fluxes, so fluxes in X, fluxes in Y, which is diffusion coefficient array averaged and derivative in X and Y direction, and then my residual, which is the balance of the fluxes minus the source term, and then my iterative update, so PF new is PF old minus the residual times my d tau, and some, preconditioning, just dividing by diagonal. It's kind of just to make sure that if it was physics, diffusion, transient, it couldn't be an array here. It would need to be max of my diffusion coefficient as in the CFL criteria. But here, since I don't care if cells don't go at the same speed, because I'm only interested in a steady state. So this would just make everyone happy and kind of converge at a different rate for any grid points as function of the stiffness, because, it's normalized locally by the diffusion coefficient. So using K max and not max of K is allowed only because I don't want the intermediate step, and I want to target the steady state. So you can run that script, which is a plain Julia script, but I just put it in because I guess it's very short and it just shows what we want to solve today. I can run it here. So, it prints and gives some, starts to make some nice graphics on the screen. So we see while we iterate, the residual goes down, and we start to establish a steady state with higher pressure here where we inject, lower pressure here where we extract, and the flux, the arrows, it's the flux, the quiver of the flux, and that's the flux here, and that's our diffusion coefficient or our permeability. And what we see, there's no flux at the impermeable barrier, and the flux obviously goes around. Most importantly is, here I have a fairly low number of grid points, so it's 63 times 127 in a y and x direction, and it takes, to reach convergence, it takes about 1,000 and x iteration, which is, it's what it is. I can say it's fairly high, but most importantly is that the number of iteration scales quadratically, because we have this explicit CFL on the time step criteria. So my time step, even if it's my iterative time step, is defined as, where is it defined? It's defined as CFL times mean of the grid spacing, and the killer feature is that square here, because I need it for diffusion stability. And so now if I increase my resolution from a factor 2, my grid size will decrease from a factor 2, and this would be squared in the time step limiter. So actually my scheme would not scale because it would scale quadratically. So now if I rerun that same code, it would not take 2,000 iteration, but kind of to the power 4. So while it goes slowly, you can play with that and maybe go the other way. So it's kind of simpler to see. We won't wait that long, but that's definitively, even at that low resolution, it takes quite a lot of iteration, which is not something you want. And on top of that, you don't want this quadratic scalability, because it would hit it's unsolvable pretty soon if you want to go with higher resolution. So we need a fix for that. And there's many ways, and I guess it's a big field of research as well, but today we'll look at a simple fix that's also pretty robust. So while the code goes nowhere, let's see how to make it to go somewhere. And so the fix is that we we added numerical time or numerical time to have something to integrate on. So no one prevents us from adding more things as long as they go to 0. So we'll add, so now we added some pseudo time on the mass balance, but now we could add pseudo time on the fluxes. And if we add pseudo time on the fluxes, we can do it in such a way that our equation turns into a damped wave equation, analogly. And this damped wave equation, the good thing is that's a physical thing, well, damped wave equation in geophysics, and we actually know that we can find an optimal parameter that would damp out the kind of wave as fast as possible. So you can really see it as an n member. If I have like no damping, then what I can do now, this part didn't change, but my flux now, I write it in a residual form and I add time stepper on the flux. And then if I integrate, if I put collapsing in 1, then you get a damped wave equation, and then this damping parameter, if it's not there, it would be a wave equation. So basically I will never get a steady state, and if it's too big, then I'm back to my diffusion process. It would take forever to diffuse. And there's a sweet spot where I get actually a very fast attenuation, like if you kind of, like in geophysics. And so that's what we do, and I won't go into details today, but there's a hopefully comprehensive paper. Like if you're interested, you can check it out. It's it's for geoscientists, so it's like for people like me to understand what I'm doing. So I hope it shouldn't be too much theoretical, but it's like based on work from the 50s by for example Frankel and Richardson. So nothing new, but it works really great. So the code, so while this one you see it still kind of goes slower. So I can now pull up the actual code that we're interested in, which is this just geothermal 2D. And so the change now is really minor. So the biggest change is that now our CFL is no longer 1/4, but it's for a wave equation, so it's 1/2. That's the first thing. And the better thing even is that our numerical time step now for consistency with unit multiplied by some wave speed is no longer squared. So it's kind of now it's linearly depends on the grid size, which gives us a linear scaling and not a quadratic scaling. And so the parameter we can play with is called RE, which is a numerical Reynolds number. So it's kind of our damping. So if depending how we vary this numerical Reynolds number, we can find an optimum. And there's a way, so by analogy to geophysics, if we run a dispersion analysis on our numerical setting, we can find the optimal Reynolds number for that process, and then we get like the optimal convergence. On the algorithm side, as I told, nothing changed here. The only thing that changed is that now we have the fluxes that previously we had Qx equals something, and now we put Qx on the other side, call it the residual, and update iteratively our fluxes as well, together with pressure I didn't mention it's and it's a kind of leapfrog type scheme, so it's sequential, and we always use the newest update for better stability. And you can see, so now if I run again, if I run this new script, what will happen is like I converge in 16 and X for 63. So it's like previously I had 1080 and now it's 16 for the same setup. It's just because I have now improved iterative scheme. And well, if just you're curious, you can mess up with the numerical Reynolds number. So if I don't know, if I multiply that by, 3, and I run it again, then it's no longer optimal. So it's still good, but it would deviate. And well, as I told, there is a way to find that optimum. But that's really interesting. So it's kind of low iteration count. And on top of that, if I now start to increase the resolution, so by a factor 2, I will get the same. So it takes longer because there's more work. But my iteration count normalized by resolution, if I increase resolution, the iteration count will stay the same or even slightly decrease. So I get linear scaling. That's pretty cool. For just this simple trick. So I just added, instead of just the sign influxes, I update them iteratively. So it's kind of 2 more fields, and that's it. So that's done for me speaking. So now I guess you can, you can try to, so we did somehow the first task, which is to play with that diffusion problem. And well, feel free to play yourself and see how it doesn't scale. And then, then we make these minor changes and then get this script that geothermal2D that kind of runs efficiently. And yeah, it's pretty dry. I acknowledge, sorry for those who wanted more details, but there is a other workshop where we had like a day, and like so if you are interested, there are like even intermediate scripts that would do the thing. So you can have a look. I've put the link there. So is there any question? Yeah.
Yeah, I have a question. On your solver, did you say that when you weakly scaled the problem, you increase the problem size as you increase your number of resources, that your number of iterations went down to solve the problem? I didn't.
Oh, okay, so the question is like about scalability, and if increasing problem size and resources, iteration number would go down. So maybe there is slightly confusion. So here it's just algorithmic scalability. So I didn't increase resources. It still runs on the CPU in plain Julia. So here it's more just iteration count to show that, well, if I increase just grid resolution, the actual number of iteration normalized by the resolution stays somehow constant, which means that the algorithm scales linearly. But yeah, here it takes more time because obviously I just run on, I guess, 4 GPU cores, and I don't use them because there is no multi-threading. So it's like single-threaded Julia, and it would, since the problem is bigger and the resources are the same, it takes longer to run. The iteration count stayed, so that was at 63 by 127 resolution. It took, well, 16 NX, and then increasing by a factor 2, so 127, 255 took a factor 14 NX. So it's kind of, since it's normalized by an X, and an X was twice larger, then it's kind of twice more iteration, but it stays like linear, and it would continue like that. And since I'm not running in parallel here, it will take more and more like actual time to solve the thing because yeah, there's more work. Yeah, welcome. So yeah, well, fair enough. We stay here with the algorithm, so the code won't change anymore now for the remaining 2 hours. So we have this code, the steady state, we solve the forward problem. But yeah, now we are like, I want to be able to, well, put in here 1023 and don't drink coffee the entire morning. So kind of that it goes a bit faster. And for this, we'll try to go towards like use GPUs. So the way we do it today, again, since it's fairly, well, it's 3 hours to go over make some cool thing, we decided to go kind of stay a bit high level, although using some performance thing, but that's still exposed as a high level to, let's say, domain scientists or even other scientists. And for this, we'll use ParallelStencil. I put the link here. You can suggest you have a look at it. Well, there is doc in construction, but yeah, most of the things are written down here. And on top of that, like so we, just as a comment, the REPL help, like the best documentation you can get for ParallelStencil is directly from this typing the question mark in the REPL. So if I have I don't know, it's macro. Yeah, so if you type the question mark, then it prints the doc string, and well, the documentation is in the doc string basically. So that's why maybe there is a README, but I would recommend you just go better with the doc string. For now, there's docs in construction, but there was like more urgent things. But yeah, so we'll use ParallelStencil and the finite difference module for helper functions. And so the idea is that we now, I prepared a script, and there it's your turn to do something. So you can pull out this 2D PS script, which has the framework of how we can do things in ParallelStencil. And your task would be to just fill in the physics based on the other code. So try to get around with the syntax in ParallelStencil. And so there we use this. So if you using ParallelStencil, finite difference 2D, then you can question this finite difference 2D, and it would give you the so this kind of math-like or math-close macros to do stencil operation. And yeah, and so in a nutshell, what ParallelStencil does, it's kind of it allows for to write code in a backend agnostic fashion, which means like, well, the code we write in ParallelStencil, we can then choose where to execute it. If you want a threaded execution, if you want an execution on NVIDIA GPUs with CUDA, or if you want an execution on AMD GPUs with AMD-GPU.jl and the ROCm stack, and then one can choose precision, so which 16, 32, and 64, and also complex number. Yeah.
When you support meta comment?
Well, I guess at some point it's metal. The only thing is that for now it's only supported in. It only supports 32 float 32s or 32-bit numbers. So yeah, I was playing in other packages with metal, but yeah, I mean, at some point when I find some time, or we'll for sure, add it as well. So that's on the roadmap.
So basically, the task is to take a look at the geothermal 2D file and try to use ParallelStencil to
Yeah, to rewrite. So what I would suggest, and I'll do is, so that's the geothermal 2D code that has the right algorithm, and the physics is here. So this 6 lines, and the idea is to populate in the code that's _PS. So the way we do it is now we pulled the physics from the iteration loop. I want to put it into functions, compute functions, and call then these, so 4 compute functions that I prepared. So residual fluxes, residual pressure, update fluxes, update pressure, and then call these functions from the iterative loop. And well, this is needed for what's called kernel programming and on GPUs. So on GPU, you need to define a function that would be executed in parallel on the GPU. That's why we need compute functions that are kind of standalone. And why there are 4 compute functions is because, so one reason is that we, well, for in parallel, we need some synchronization because since we do, well, derivative of fluxes and then to update pressure, derivative of pressure to update fluxes, we have to ensure that everyone is up to date before we use what we computed. So that's one reason for, well, preventing race conditions and having correct execution. But one could do it in fewer kernels. The reason here I have 4 kernels is that I need for automatic differentiation later, I need my I need function which define the residual explicitly somehow to be able to pipe this through automatic differentiation. And this is why I cannot here, at least for now, I cannot fuse the kernels. That was what I was looking for. So yeah, so the task is to complete the calculations here, and yeah, as I said, so you can use, if you make if I use the finite difference module, then I can also question what it's doing, because that's what I should use. So let me pull this up bigger. So yeah, what the finite difference module does, it defines conveniency macros to perform stencil operation. And so what we can see is that, for example, this averaging here, averaging in X, would, for example, need to be replaced by average in X, and this A means that I take the average in X and I don't take, for example, inner point in Y, I take all the Y direction points. And this one, for example, would be averaging in X, but from 2 to n minus 1 in the second dimension. And yeah, and there are some other functionalities as well. And so I guess now for this task, we need the averaging and, well, those one here, which selects all my array, the inner points in X or the inner points in Y, and derivatives, like derivative in X. So that would be, this one here would be diff of something, dims equal 1, and that would be diff dims equal 2. So I can get started here. So for Rx, what I have, so I have kind of Qx, and Qx would be the same as Rx, so it's inner points in X, and so on. I can go, then I have average. So in ParallelStencil, there's not functions, there are macros. That's why there's this at in front. And I can also remove the dots because it's no longer broadcasted, because this will be now. So what ParallelStencil does under the hood is, like, if you execute it on threads, it would, like, pre-processing add a loop around the statements and expand the macros to the finite difference operators. And if it runs on GPU, it would, like, transform the kernels and inject the kind of block and, like, the GPU parameters to get the vectorized indices. So the code is there's no longer vectorization needed here. So I can just remove the dots, and this would be my at the X. Yes. Yeah, and so kind of the only thing to take care is, like, my arrays, there are, like, different sizes because of the staggering. So for example, the fluxes is one larger in X because I include I control the boundary condition here with Dirichlet condition on the flux. That's why I have a larger array. So yeah. Then we can do the same here. Q1. And then yeah, on top of that, so once I'm done, let's say, with one of the function, I just have to make sure also to pass to the kernel or to the function the arguments that I need. So here I would have, I always already put in what's returned, the first argument, and then it's not that's needed like that, it's just my own convention, and pf and then dx dy, and that would be one kernel here. So then I can just make sure that I copy the arguments here. Hopefully didn't mess things up. And then I have also to pass them here. And then that would be the first thing done. So then I can just quickly finish.
Sorry,
Yeah.
what is that function d underline xa do, and the other ones with the I one?
So I guess normally if you type here at AV,
But it's in one pattern. Oh, AV. Okay, my eyes are seeing that.
yeah, so it computes average between adjacent elements of A along the dimension X. And then if you want to pull the inner, it's the same, but it's inner elements and all with the other definition. So all the macros, you can query the functionality with the help. It gives you the, but yeah, I guess with this first function, then the pattern is pretty obvious. So I'll just, so RPF is this guy here. And yeah, if someone needs, well, I guess, yeah. If someone has a question or needs help, you can just raise hand and we can also pass by quickly. I'm quietly doing the thing on my side. So, well, for those who did along, you feel free to continue. I'm kind of mostly done. Didn't test it yet, but yeah, maybe just a couple of words. So, because of, well, it's like other backend agnostic packages, for example, well, kernel abstraction or maybe others. The idea is that it's portable across different architectures and type of architectures. So, but well, GPU programming is more restrictive in a sense, I guess, than CPU programming. So it's, well, the code is, you may have seen it or not, but it's kind of GPU biased. So for example, well, that's also the reason why in the compute function, they don't return anything because that's not allowed for GPU kernels. So you have to, that's why the function names, well, I guess you're all familiar with that. All function names, compute function name have the exclamation mark because we actually mutate arrays that are passed. So it, yeah, we don't create array or return anything in those functions. They just do work on arrays that we passed to. Yes, there's a question. No, yes, exactly. So yes, so there's no longer broadcasting because now that's taken care, as you say, by ParallelStencil. So how it works under the hood is that well, these find a difference macros, well, one can look in the source code. That's just boils down to actually explicit, well, difference macros that were tested and programmed once for good. So, well, differentiating, taking averages, etc. So that's replaced by these things, and then it's most likely, well, depending on the backend one targets, it would around, so the statement they're expanded, and then if it's for CPU, there will be a loop around, so it would turn into a well, loop-based code. So
and then combining the results, or trying to, is there a way to kind of like at the compile level, does it try to kind of optimize the code generation there?
Yeah, well, it's macro, so it would generate code, and then the code will be compiled, so it would benefit from all standard optimization that Julia does for loop-based CPU code, for example. And if it's GPU code, it would generate GPU kernels, and then, well, the GPU compiler pass will also be able to optimize, like if you had written a CUDA kernel in Julia. And there is some, well, there is now some internal optimization done by ParallelStencil, for example, that were recently added for example, to tackle, to use shared memory and register queuing and all these things. But so the advanced optimization, some are listed here. That's really rather now we focused on GPUs because that's kind of the main target. The reason, so the CPU backend of ParallelStencil uses multi-threading. So it has this, it use threads at threads. So you can set like multiple threads in Julia and it will try to use it. But we didn't push the CPU-based optimization really far because, yeah, our focus is GPU, but it's useful to have the code to be able also to run on the CPU. Mostly, at least our usage is mostly for development purpose and prototyping. And then when we're happy that the code does what it should do, then one can deploy it on, well, multi-GPU thing. So that's a bit our workflow and what guided the design of ParallelStencil. But like the CPU code works just like multi-threaded CPU code in Julia, and so which means it works fairly good.
So I would assume that can you get more mileage if you were just writing
ParallelStencil allows you to switch easily between, for example, NVIDIA and
Yeah,
AMD and so on. But if you write your own kernel, would it be competitive or faster? Or?
Well, the ParallelStencil now is as fast as kernel written in plain CUDA or plain AMD GPU, and in some cases, since in ParallelStencil we have some you correct me if I'm wrong, but at least targeting on the GPU backends, some mostly now spend quite an effort to include advanced optimization, automatic optimization that you would get if you write it in ParallelStencil, and that you would have to, write on your own if you would write it in plain CUDA. But so in that sense, for use cases on NVIDIA GPU, at least that we could test, we get better performance with ParallelStencil than just writing it in plain CUDA.jl, just because, not because it's magic, but because ParallelStencil does for you some advanced optimization under the hood. So mostly a shared memory usage and register queuing, analyzing the pressure of the kernel, and then choosing some good way to queue things. So, and in that sense, for some use cases, you get better performance with ParallelStencil than in plain CUDA. But again, if you would write this advanced optimization in plain CUDA, then it's at the end it's what's done in the back. So you should get back on your feet. Just like for humans like me, I don't spend my day trying to write register queuings in GPU kernels, because I need to use that to, for example, do some geophysics and some other things. So that's where it's really helpful to get those kind of that package, for example, where I can then just write my code and I know it will mostly execute very optimally on the GPU. But thanks, that's a very good point that you.
Maybe I can add just one thing. So of course, if you're a specialist and you want to spend a couple of months, or I don't know how much, or half a year, and making a code super fast, one specific code, you can get a better result. Of course, right? Because in the end, this ParallelStencil produces a CUDA kernel. You can write it yourself. If you know better how to do it, you can get something better. But still, you also need to consider that if you have some complex application, these kind of techniques become so quickly, so impossible to write as a human, or at least incredibly complex. And so it's a benefit to have some kind of meta programming which does that for you.
I don't want to get into the, one doesn't want to get into the nuts and bolts too far into, it's a rabbit hole to go down all of the little bits and pieces of that. So, just staying at the high level, this is brilliant. This is fantastic.
Yeah, that's a fair point. So again, I guess that's a good, thanks for bringing up that discussion. And so maybe one thing we try to do here that differs from maybe, or at least what we try to ensure is that usually high level tries to target portability, or that you can abstraction, and that you can do many different things. And then at the end cares about performance, and then it's a kind of very hard fix to go back and fix performance. So here we tried at least to get the opposite way, to make it high level, but really first performance and somehow then features and portability, because, for our work and our usage, it really matters that we get the good performance and keep that good performance when adding features. And if a new feature kills performance, then we rather don't use that feature, because, then it kills performance, which is the first goal we want to have. So that's a bit the philosophy behind. So maybe in the meantime, so I kind of did my little homework thing here. Yeah, one thing to be careful is that it doesn't, so in the residual, I assign things to my residual here, but in the update, I need to, update my fluxes and pressures. And previously in that 2D script, sorry for switching around, I had this contracted operator, so minus equal, which, well, this we can fix in ParallelStencil, but for now it doesn't work, at least in that, using this way of writing the kernel, so you need explicitly to say that, well, qx equal qx minus the rest, because we cannot contract the operator here. Just a heads up. But that's it. So mostly once you're done, like with writing these 6 lines and filling the arguments, and also making sure they're reported here, I guess one could try to run the code. So that's the one I just had here. So include now geothermal to the PS. And yeah, and one important thing is at the top of the code. So obviously I can select the which backend I want to use. And while here I want to run, I'm doing it to my GPU server. So obviously I want to run it on CUDA in double precision to get like good convergence. And yeah, so we can select this, and let's try to see if I kind of did a concentrated enough by doing it. Yes?
Over here.
Yeah.
Stefan, my name is Stefan. I'm not so much into ParallelStencil, which time for me, but I'm very curious. There's a lot of macros, and it seems quite restrictive that ParallelStencils give us. Like we cannot use the normal Julia syntax any longer, but we really need to get a specific macro for every single operation. Can you explain a bit why this design choice is needed?
Yeah, maybe you can.
Yeah, so the basic idea is to have some mass-closed macros, such that we can write equations like we see here to solve geoscience problems or whatever, right? Just write down PDEs, for example. Such a basically a function is just writing down some equations. And we will even push further the syntax in the future that you really can write basically equations. So that is the first idea. Then we have something else, it's called parallel indices. If you're familiar with that or you have seen it, where you can explicitly write kernels. So you don't have to use these macros. So there you can do whatever you need to do that you cannot do that way. And this is basically the idea is when you cannot write your equations with these simple macros, then you have an alternative to do whatever you need to do.
Okay, so it's actually something on the roadmap that the macro could even be a bit more user-friendly, so that we don't need all these specific average diff and support macro, but we can use a bit more standard Julia syntax.
No, this would be then what I meant is that would be on the roadmap is that we could really write equations as in math. Huh? But already now we have something else called parallel indices. Can you show the doc?
I pulled it up here. So that would be a kernel written in parallel indices where you can explicitly pass indices, and then you're free to do whatever you want. So you can write indices, like you can index things like there, basically, for example, for this code here versus a standard function with a double loop, the only thing you omit the loop. So you will have just to handle the bounds with some if checks, but the rest you're free to do whatever you want. So you can use your own macros, define new macros, inject inline functions, use plain thing, and that would be more. The idea is that at parallel, without indices, so the at parallel function only accepts these mat close macros and is a bit restrictive, meaning that if you use it, you're pretty sure that you would get good performance because it's restrictive, but for the purpose that everything you will do with that restrictive syntax will ensure good performance. And then if you know what you do, or if you need more flexibility, then these macros and at parallel, you can just write at parallel indices, pass indices, and then you can do everything you're doing in a standard CPU function or GPU kernel, so whatever. Then there is no checks. If you don't check the bounds, it won't do it for you neither. So you would get seg faults if you do out of bound access, etc. So yeah, that's kind of the, I guess, 2 levels. So the higher level, let's say API, which is restrictive, but yeah, there's no big, yeah, you can't do anything wrong, and you would get like the good performance. And then yeah, if you need custom things or know what you do, then you can go with a more with a standard, like say, more permissive syntax and do whatever you want in there. So and both are like fully supported.
And so this is really like CUDA kernel programming, the way you do that. Just the IX, IY, for example, there you just get it, while in a CUDA kernel you would have to say IX equal, and then something with block ID, thread ID, etc. Right? That's it. So it allows you to do anything you could also do in a CUDA kernel.
Thank you very much for the details.
Yeah, well, thanks for the question. Like that's.
Yeah, please.
Can I ask about this parallel indices? Is there a way to do reductions as well?
Reductions are not there are no like features specifically for that, but you can do it yourself, like you would do it in CUDA, right? With you have also the possibility to get block ID and thread ID, etc. You can also shared memory explicitly use it, and so you can have the basic tools that you also have in CUDA. Now you don't have the full set of functionality as in CUDA. You have only the basic ones.
So well, here would be, that's one of the scripts that would be the parallel indis script that does Laplace, well, again, the diffusion step, but kind of using explicitly shared memory, but kind of from the parallel stencil framework. So in a parallel indis kernel, it's really like, it really looks like CUDA, with the only difference is that, well, things are wrapped into macro and we omit, so you don't need to query the indices like from the vectorized CUDA domain. But yeah, you can access thread indices. There's the shared memory access, block dim, and so you can sync threads. So in that sense, it's really, as Sam said, like parallel indices is really the same as you would get on GPU. And well, if you wonder on CPU, like most of these things may not, it may be very different. So then that some of the things would just be, it would still run on CPU, it would just become no up and not use actually shared memory, etc. Or if, for something we have it on the CPU because it was kind of tractable to implement. But yeah, since focus was on GPU, so still the code would run on all backends. That's kind of the main purpose, but always optimized for GPU, and things that are not available or conceptually would be totally different on CPU, it would just becomes no ops, and we keep only what's, well, to get the right result, but then not the full support. Cool. Yeah. So maybe, yeah, I just quickly comment what I run, and then take your question if that's fine for you. Yeah, so just, I had a mistake here. That's why it blows up. So I had in X, but it's in Y. So the code is there, and now basically I can run it on my GPU, and yeah, well, it runs here in this 14 iteration. But now I can, try to increase the resolution, and it still, well, runs fairly fast. Again, we won't measure performance in details today. That's beyond the scope of the workshop. But like one would need to deactivate plotting, etc. Because now most of the time still is taken to draw now a high resolution PNG thing. But yeah, I mean, I can just, from running it, we see that, well, basically it goes fairly fast now for 10 folds. So that's now 1,000 by 2,000, and I guess it will run in a couple of seconds. And, well, still my scaling holds. So you'll see I get like 40, 16 NX. So I had it on 63, on 127, 511, 1023, and I'm still at between 14 and 16 NX. So kind of just to call back to the algorithm part, it's the scaling holds, and now I'm on GPU, and kind of the execution time is also at least order of magnitude faster than on the CPU. So that's kind of somehow for the forward problem. That's what I wanted to, or we wanted to share with you, is now there's a way to get an efficient algorithm that also efficiently runs on the GPU with a fairly concise code. So it's like 4 functions, about 10 lines of the physics, and there's no hidden things. So there's no call to solvers, etc. It's all self-contained in that code. And yeah, again, like the code is only about 100 of lines, minus the plotting, it's even shorter. So kind of thinking also a bit about, well, we are a researcher, like teaching some people, supervising students, etc. It's like to get the students started and doing research done with such type of approach, it's kind of much faster somehow than if someone has to dig in a huge code base, start to understand before being able to make changes, etc. Then here you're better off, like, while talking to you and discussing some stuff, I could program most of that like in a couple of like tens of minutes, and it's working. So just kind of a bit like zooming out beyond that workshop, I guess that's also nice somehow philosophy that I personally like and support, to have this more like building blocks thing, and then just combine them to get what you want, and maybe write more specific code. But yeah, like your question.
Did you guys take any inspiration in the video package? The video. Have you guys ever heard of it?
The Vito?
Yeah.
Yeah. Well, I know it, but not really. I guess it was a parallel develop, so separate development.
I see that you guys go in the different direction. The video, it does what you meant to do, right? You write the equation, and then it creates the code for you. But I think it goes top, bottom, and you guys go bottom up, in the sense that you guys go from the stencil and you move towards like a language that you can write the stencil, a kernel that solves the final difference code. And they go from the equation, they go down. But I think when you do that, you lose some control, right? The user doesn't have this kind of fine-tuned control over what he wants to do. I think your approach is very good, and you prioritize performance, which is really good. But I just wanted to ask if you guys have any kind of inspiration, but it seems like.
No. Well, that's a good point to bring that up. So no inspiration, but at least I know that's around, and I have colleagues that also use it. And I would say maybe I don't want, we can speak later about like the pros and cons, etc. But definitely one thing that's good with packages like the one you say is that, well, indeed, you write somehow, it's like Phoenix, you write your equations, and then it takes care of the rest somehow. And that works fine. Well, that works great for classical thing, and well, actually things for it was designed for, because well, someone had to program what's going on under the hood, obviously. But these things, in some sense, break down when you try to do things it was not designed for. So when you try, for example, multi-physics, and try coupled things, so fluid diffusion, maybe heat diffusion together, and then deformation, nonlinear interaction, localization. Well, then it will choose things, but it will be pretty much, I guess, both on the performance and algorithmic level, it might be not optimal, and there you hit some, hard stop, basically. And so that's why we kind of tried to take that maybe perpendicular approach, because, there's other cons, but there you have other pros.
Can you quickly show the zeros here? Just one comment to you and the previous question about reductions, for example. So these zeros here, this will create normal CU arrays, for example, for CUDA, or normal arrays for threads. And so this means that you can use with these arrays the usual GPU programming. So you can do reductions with the functionality of CUDA GPU arrays, right? If you go to CUDA.jl, you search, how can I do a reduction? That's what you can apply as well. And so in that sense, also we try to have something that integrates into the whole Julia world, where you can use other things. And as you will see later, automatic differentiation as well, which is something mind-blowing. It has nothing to do with all that, and it just works, right?
Yeah, that's a fair point. So yeah, well, here, so I guess if we go back now to the materials, so we are done with this task 3, and well, ideally, well, I have it. Ideally, for those who did the exercise, it's working on your side. If you want to try hard to make it work without looking at the results, or if you have still issues, I guess after the workshop, I'm most happy to sit down and check out if for someone something is not working as it should. But I mean, just for a purpose of, well, staying on time and keeping up with the schedule, I suggest we move on. Question, do you want a short break, or shall we just go on until noon? If we just go back to somehow our little roadmap of the morning, so we did the part 1, which is focusing on the forward problem, which we just solved now. And I mean, for those who stayed along with the little exercise, you should now have a 2D code that's kind of can run on CPU and GPU that implements like a kind of accelerated algorithm scheme to solve an elliptic problem, and that's well produced the figures that you saw. And so now I will head over the mic to Ivan, who will basically guide you to the part 2, which is actually using making optimization problem, doing an inversion, and at the core of the inversion, you need a fast forward solver. So that's why we first look at the forward solver, make sure that we have a fast, scalable forward solver, and now we look at kind of maybe a bit of fresh way how we can do an adjoint-based inversion using, like doing minor changes again on that forward solver. And so that's Ivan's part. And then at the end, in the wrap-up, I'll show the final kind of achievement, which is like, okay, then we can push the thing even further. And our GPU-based inversion that is powered by AD can, like with a couple of more functionalities, just kind of run on multiple GPUs somehow out of the box. The main feature, as Ivan will motivate it, is that we call AD on a very internal functionalities, such that, well, we don't need to differentiate through loops or through MPI calls or whatever. And that's kind of, I guess, one of the power of that approach. So yeah, I'll don't spoil Ivan's content. So yeah, Ivan, you can go ahead.
Okay, so thanks for the introduction, for guiding us through the first part. So yeah, I'm sorry that I couldn't be with you in person here today, but I hope that won't be a big issue. There could be two smaller issues, though. The first one is that the internet connection is a bit unstable, so if you will hear some stuttering or whatever, if you couldn't hear me, please feel free to interrupt so that I could repeat it. And the second small problem is that I really don't hear the questions from the audience at all. So yeah, you will need to kind of really, yeah, feel free to, I don't know, interrupt Ludovic or Sam, and so that they could maybe repeat the questions to me so that I could answer. But otherwise, I think we should be fine.
And yeah, I suggest to start. And in the beginning, let's look at what we achieved now. So if we go and check the illustration, yeah, what we actually know how to do is that given a setup, right? Given that we know everything about our problem, so the geometry of the domain, which is just a box here, knowing the positions of the injection well and extraction well, and all the fluxes, and the most importantly, the properties of the subsurface, which in that case, we reduced all them to just one scalar field, which is the permeability. So that's basically the resistance of the rock to flow. So how interconnected are the small pores and voids within the subsurface are. In reality, it's much more complicated, of course, but here we are trying to simplify things a bit. And yeah, this is a very important quantity in many applications with respect to the shallow and not only shallow subsurface. So, and the problem with these things is that they are usually very poorly constrained. So to measure this permeability fields, you cannot do that directly. You need to drill Earth's, well, the shallow subsurface to extract the samples of the rock, and you need to do measurements in laboratory to determine experimentally these fields. And yeah, this usually leads to the fact that our knowledge is extremely scattered and very uncertain, especially if we try to go deeper. When we extract these samples, we can we change the pressure, the confining pressure of the sample, and that could lead to the destruction. So there are so many small bits and pieces that lead us to the big issue in all this problem. So, however, there are other things that we can measure directly or almost directly with good spatial and temporal resolution, and these are usually what we calculate in our model, right? So, for example, around our wells, we can measure pressures and fluxes relatively easy, and on top of that, on the surface, right? So on the where the depth is equal to 0, we directly see what's going on with the surface, and if there is any manifestations of the processes that are going below the surface, we can measure it with a good resolution, right? With remote sensing, I don't know, we can put a lot of GPS trackers, we can put satellite imagery, so we can use a lot of that info. So, and it would be really cool if we could calculate the properties of the subsurface of what we don't know based on what we know and can observe, right? And that brings us to the idea of the inverse modeling. So now we go to the second part, optimization problem, and here I want to introduce a little bit of terminology, right? So we will call the forward model the model that you have just implemented, right? So this is a mapping that takes as an input everything that we prescribe. So, for example, the permeability in that case, or it could be geometry, it could be anything, any free parameters to our model. In that case, it's permeability. And as the output, it gives us the solution, right? It gives us the fluxes and the pressures. So what you have computed in the first place, right? And the way how this mapping, we call it this calligraphic L, and the way how it works is that it makes the residual go towards 0, where the residual is defined as basically the the left-hand side of our equation. So what should go towards 0? Another way you can put it is you can figure out some external principles. So for example, we can minimize the norm of this residual. And that would be, for example, the exit criteria that we use. When some norm of residual in some metric goes below a predefined tolerance, we stop the calculation. So we call this the forward model. And then we can identify, or we can quantify the discrepancy between the results, so the outputs, which are the fluxes and the pressures, and the results of some observations, right? So, for example, assume that we can monitor at some sparse collection of points, of spatial points. We know what other pressures and fluxes in real life or in some artificial setting. And we introduce the objective functional, or in finite dimensional case, it will be objective function, which measures in some way the discrepancy of the results of a forward model and the observations, right? In the simplest case, it could be just this kind of L2 norm or something similar to L2 norm, so just the square, the integral of or the sum of the square of the differences between the results of a forward model and our observations. All right, and this is called the objective function because the ultimate goal of the inverse modeling is to find such a distribution of the parameter of any free parameter, in this case permeability, which would minimize that objective function, right? So we want to vary, we want to change the input to our free model, to a forward model in such a way that the outputs, that the discrepancy between the outputs and the observations is as small as possible with a given metric, right? So yeah, in this way, you could imagine the inverse model is basically going in the other direction. We don't start from the inputs and get to the outputs. We do the other way around. We start from the outputs and we try to compute the inputs. How do we do that? Well, this definition somehow kind of implicitly assumes that we want to minimize that objective function, which leads us to the idea of mathematical optimization. There are many countless ways of minimizing functions, starting from the most primitive algorithms like brute force, right? If we have a low dimensional problem, if we don't have, for example, if we say that we know that the permeability everywhere in the domain is a constant, then we can just set up a grid of parameters and we can sweep over all the parameters of a problem and just make one forward simulation and then pick the one that gives us the closest results to the observations. But in many cases, we have spatially variable fields, and when it comes to the Earth subsurface, this is a kind of multi-scale problem, which leads to the fact that usually the properties of the subsurface, they change drastically in space, and usually by many orders of magnitude, right? So the typical permeability ranges for the Earth crust, they range from 10 to the power of minus, I don't know, 20 towards 10 to minus 10 or something like that. So it could be it could be tens of orders of magnitude in difference. The same goes for all other properties like viscosity, etc., etc. So we cannot really afford the brute force in many practical problems. So the same goes about all other naive ways of computing this minima, right? So if we have a higher dimensional problem, for example, we want to invert to find the distribution of permeability at each grid point, right? So if you have the resolution of 500 times 200, or well, 1000 by 500. This means that we have 1000 times 500 degrees of freedom. That's where we can change our permeability. So the number of independent dimensions is really, really high. So yeah, then we have to resort to some kind of local methods that would be much more efficient than just the brute force. And yeah, the most well-known methods are gradient based, right? So there are gradient free methods, but they are also pretty time consuming. So if we can get a hold on the gradient information, this makes the inversion procedure much more efficient. And the basic building block of all the gradient-based methods, or I don't know, the prototypal methods, would be the gradient descent. If we just go and check what it is, that's maybe, I'm pretty sure that you know all that, but I'm just giving you a quick recap, right? So for example, if we know the gradient of an objective function, we can start from some initial approximation to our parameter, and then we can just iteratively update this parameter with the gradient of the objective function in some scalar, which can be a learning rate, is called a learning rate or step size or whatever. So yeah, on this figure, you can see that we start from somewhere, and then we go towards the direction of the steepest descent of the objective functions, the isolate, which are shown here, right? There are many other fancy methods. For example, if you have the higher order information, you can use the Newton solvers, which could converge much faster. And but there are other gradient-based methods. For example, quasi-Newton LBFGS methods, which approximates the second order information from just having the gradients. And so this is the methods that we will use today. So now the next question that arises is, what is the gradient of the objective function, right? So with respect to the parameter. And that's actually a tricky question, which usually would require, well, some knowledge of functional analysis. So then we would need to, well, recognize that this function actually accepts another function as a result, and it gives a scalar, so that would be a functional. And the derivative of that objective function with respect to the parameter is it depends on the solution. So it's not just a function that directly maps the inputs to the outputs. It's a function that first requires a forward solution, which is given to us implicitly as something that makes a residual as low as possible. So then the computation of this gradients is not really straightforward. However, there is a nice trick. There is a nice mathematical trick for doing that, which is called the adjoint state method. And unfortunately, I don't have enough time to really dig into details about what it is and how it works. But just in short, this is the method that allows us to efficiently compute the pointwise gradient of the scalar valued objective function. So our objective function is a scalar value. It accepts the entire field of permeabilities, right, the pointwise distribution, but it outputs only one scalar value, which quantifies how far are we from our observations. And for these functions where the input dimensionality is much higher than the output dimensionality, you can use this adjoint states trick. You can read about it on Wikipedia, or you can read this derivation here. I hide it under the summary, the detail tag. But yeah, in principle, what it is just a Taylor linear expansion of the solution around some reference point in the parameter space, which we then kind of can solve an additional linear system of equations, and then we can calculate the gradient of the objective function, so this dj by d Okay, so there is the derivation you can read. You can go through it if you really want to understand why and how it works and why it is more efficient. But I won't dive into details. I will say that in the end, we will have, well, let me show you kind of equation that looks like this. For every independent variable that we have in our forward model, which are fluxes and pressures, we will introduce the so-called adjoint variables, for which we can write another system of equations, which would be exactly very similar to the original forward system of equations, with a kind of small difference that this is actually would be a Jacobian, the transposed Jacobian matrix of the original system of equations, and with some right-hand side. So ultimately, we would need to solve this system of equations, and there is a kind of very nice property of this system is that it is equivalent to the linearized original problems in some, well, exactly predefined sense. So it's spectrally equivalent, which means that we can use the same pseudo-transient strategy to solve in this adjoint system of equations. So we just kind of augment the system with pseudo-time, the derivatives and pseudo-time of the adjoint variables, and then we can time march this the system until convergence. So that's, in that sense, the only information that we need is the result of the application of this transposed Jacobian matrix to the adjoint variables. And luckily for us, so before now, this would either require some specialized software which we could generate from the source code, this kind of things, these evaluations, and it was available in Fortran and C++ to some degree, but it wouldn't work. It was very problem specific. It wouldn't work, for example, with GPUs, etc. And now with Julia, which is a killer feature of Julia, really is that we can now compute these expressions knowing just these functions that we want to differentiate automatically using automatic differentiation. So, and in the end, yeah, we will our gradients will be just kind of this expression, which could also require us to multiply vectors times Jacobian matrices, which we can also do automatically, and this is what we will do. All right, so now I will say just a couple of words about automatic differentiation. I'm pretty sure that, well, many of you already know what it is, but we will still kind of do a quick recap. So that's the technique that can evaluate the gradients of functions which are specified by code, so not as abstract mathematical functions, but just the standard codes, and automatic differentiation will repeatedly apply the chain rule of differentiation until we go down in our codes to the most primitive elementary arithmetic operations which constitute a computer program. So yeah, if we can do that, that would be called differentiable program. So that's a paradigm which enables gradient-based optimization of the parameters of an arbitrary computer program. And Julia is at the forefront of this paradigm. It has a rich support. It has, well, it has many packages for automatic differentiation, but for our purposes, only Enzyme.jl, which is a package developed at MIT. And yeah, it makes it possible to compute derivatives of arbitrary Julia code, including the code targeting GPUs. So yeah, you're welcome to read about it more, but we will just go directly to the examples, right? We will try to get a grasp of what it is. So now I'm switching to the REPL, and here, yeah, I will use Enzyme, and we will just kind of write a simple function.
Sorry,
Yeah.
can you maybe slightly increase the font size?
The font size, yeah, sure.
Super.
Is that better?
Yeah, thanks.
Okay. Yeah, so for example, we will write a very simple function f, which would maybe accept a parameter omega and another parameter x, and it would just compute the sine of x, right? So we know that, for example, pi 1 would be very close to 0, right? And we can actually evaluate we can compute the derivative of that function manually, so there is no really big need for automatic differentiation. We just know from the basic calculus this would be this, right? So if we compute
Can you further increase
the
font size?
Yeah, sure. I guess.
Thanks.
All right. Yeah, I can close for now the button pane. Yeah, so kind of exactly what we expect. And now let's try to achieve the same result with Enzyme. And well, the basic operations that we need is enzyme autodiff. So you type enzyme.autodiff, and here you, as the first argument, you pass a thing that's called mode of differentiation. There are two, forwards and reverse. Unfortunately, I don't have time to dig into details, but yeah, basically it's where we start applying the chain rule from the start or from the end, and you will need actually a reverse mode in this workshop. So I will type this. Then you pass the function name, and then you say what you just pass the variables, and the variables should also have things that are called activities. So, for example, we don't want to evaluate the partial derivative of this function with respect to parameter omega, so we write const. However, we want to differentiate this function with respect to the second parameter x, which means that we need to make it active. And yeah, something like that. So let's try to call this function. Now we'll have well, 1.0, and yeah, unfortunately, I need to specify. All right, so yeah, we see that it returns, well, the tuple of the tuple, since it returns nothing for the first argument, which is the partial derivative with respect to the first argument, which we explicitly said that we don't want to evaluate it, so it returns nothing. And as the second argument, it returns something that is actually very, we already know that this is the answer, actually. So if we compute the analytical function, then we see that we have absolutely the same answer, right? We can verify that. So yeah, kind of this is basically this is it on a very high level. So if you have any function, which can be, of course, much more complicated, that's what we wrote here. So it can contain loops, it can contain system calls, it can contain whatever else, and Enzyme will still differentiate that function. So this is somehow, well, this is close to numerical in many cases, because this tremendously simplifies writing the optimization algorithms for us. So yeah, now we know how to do it with the scalar valued functions, and the next step would be to do the same thing for vector valued functions that mutate their arguments, right? Because in the end, the kernels, the parallel kernels that you wrote, for the forward problem, what they do is that they take several matrices and they mutate some of the matrices on the way. And we need to be able to differentiate this code. So we can do that, of course, in a plain enzyme, but we're working with ParallelStencil. Here in ParallelStencil, its recently added feature is kind of a very simple and elegant way to automate, to make it even more high level. So let's do this. So we can use ParallelStencil, and yeah, for example, we can initialize it. It's ParallelStencil, threads backends, 64. 2, well, it gives me the warning because it's already initialized. That's not a big issue. So I will write now a simple parallel kernel, which will do exactly the same thing.
Ivan,
yeah.
Sorry to interrupt. Yeah. There is a question in the room.
Yeah.
The question is like, what would autodiff return for apps of X?
Yeah,
that's a good question. So let's check, because different packages, they have different tie-breaking rules, right? And some packages would just return not a number or something like that, and some would pick some tie-breaking rule. And I'm not sure what Enzyme would actually do here. And let's try. So enzyme autodiff reverse f, and for example, yeah, see. So if we're positive, again, and reverse. If we're positive, it's 1. If we're negative, it's -1. And if we are exactly at the singular point, then yeah, here you see picked as a tie-breaking rule the positive derivative. And yeah, in some cases it could be what you want, because if you have singularities, then you usually in the code you want to resolve them in some way than just silently failing and ruining your simulation. But yeah, different packages choose different approaches. Okay.
Well, it's always defined for singularities values or?
Well, I don't know for Enzyme. So for different packages, usually, well, for the forward diff.jl package, for example, it's defined, and I guess it used to return nones always. But for Enzyme, I'm not sure. So it's better to, and it's not part of the documentation as far as I know. So yeah, I guess the best you can do is to try, or to try to ask the developers. So yeah.
Thanks.
All right, so let's go back to the parallel, writing the parallel kernels. So for example, if we now write another function that would be at parallel, and it will compute the same thing, right? So it's omega x, but now this time omega is still a scalar, but x and r would be matrices, and we will store the result in the first argument, right? So according to the specification, we have to return nothing from the parallel kernel, and here we also need to say that all r is equal to sinus of omega times at all x, right? So yeah, I guess we can. No. All right, and now if I use zeros, well, for example, 2, 2, and x would be some random value, and well, let's say that omega is still fine because why not? And now we call it parallel and I will pass it like this. Then we see that we now store the results of the computations in place. So how do we approach the automatic differentiation? Well, we will need to introduce some extra storage for partial derivatives and for the value at which we evaluate our derivatives. So usually there is one of the conventions is that these extra values have the bars over them, which we use now. So example, let's say once to 2. So that vector would be, it's associated with a return value, and it will store basically the vector in the vector Jacobian product, right? So because the partial derivatives of the function that accepts a vector or matrix and returns a vector, the partial derivative would be actually the kind of the Jacobian evaluated at some point. And if we're using the reverse mode of automatic differentiation, it will be actually the kind of the transpose of the Jacobian times vector. And it has to do with the fact that reverse mode starts from the end of the kind of the calling chain of the functions. Unfortunately, I have no time to dig into the details, but kind of you can intuitively imagine as if function f it starts from evaluating the innermost arguments. For example, if in this case it's sine of omega times x. So we start from x and then we propagate this information outside, right? We multiply by omega, then we evaluate sinus, and we assign it to r. Then the reverse mode of automatic differentiation, it starts from the ends of this chain and propagates the information in the opposite direction. So it will start from some kind of tangent vector associated with the results, which would be the vector in the Jacobian vector transpose product, and then it will kind of push it all the way through the beginning of the call chain and store the resulting partial derivative in an extra storage vector associated with the x variable. So it may sound pretty convoluted, but I guess when we go to the examples, it will become more clear. So, for example, we want to multiply the matrix which consists of all ones. We want to multiply the partial derivative with a kind of Jacobian of the function, and store the partial derivative of the results in this variable x bar. Okay, so now we want to allocate. So now we have r, we have x, we have r bar and rx, and now we can exactly as we called in the first place the like the primal kernel, which computes the primal results. We can just pass one more keyword argument null1, which would mean that we compute not just the function itself, but also its partial derivatives along the way. And then we need to map the primary variables to their corresponding this extra or adjoint or shadow variables. It has many names, but the meaning is the same. And so the syntax is as follows. So the first argument is the primary variable, primal, and the second is the corresponding adjoint variable. And we do the same with x, so xr. And if we don't put anything in here, and then it will, by default, it will say that this variable is a const, right? Which we do here. And now we evaluate it. And now if we look at the adjoint x, it has something in it. And if we compute the analytical results, and this function is very simple, so it's Jacobian is just the diagonal because it's just a pointwise application of the function. So we actually know that if we take omega and we broadcast multiply by cosine of omega dot x, we actually have the same result, right? And we can actually verify it. So it's true. So in this very simple way, we can actually compute transposed, some vector, which would be stored in the variables associated to the return values, and we can propagate that derivative information using Enzyme automatically throughout the kernel and store the result in these vectors. And kind of the important kind of detail is that Enzyme accumulates by default, so it takes the partial derivative information and it accumulates it in the vectors that are associated with the results, with the input variables. So you need to initialize the storage, for example, with all zeros if you want to have a pure information, which is what we did here. All right, so yeah, hopefully it was pretty clear how it works. So it's, as you can see, it's very simple, but it's actually a very powerful technique, right? Because your function f, it can contain arbitrary code. It can be as nonlinear and complicated as you want it to be. So it can have our finite differences, or it can have your finite elements codes with, I don't know, numeric integration, assembly, and all kinds of things, and it will still go through all of them and give you the result. And you can do much more than that, of course, but this is out of scope of this presentation. Okay, so now I think that we're pretty fit to start the hands-on activity, right? We plan to implement the gradient-based inversion algorithm for the permeability of the subsurface. What we will do is we will assume that we have some observations. Of course, we don't have any observations, but we will generate them. So we will start from the permeability distribution that we had in the first place, in the first part of the workshop. And then we compute the pressure and fluxes distributions for that solution. And then we will assume that these are our observations. Then we will record these observations only for pressure. So in this workshop, we only do this we assume that we only know the values of the pressure. We put the barometers somewhere in the subsurface or the surface, and then we know the pressure. And then we will forget everything that we know about the original parameters of the problem. We will forget that we had this permeability barrier. We will assume that we know only the values of the pressure. And here, I guess it's the best if I show the plotting pane of Julia. So yeah, so this thing over here. Okay. So yeah, so this is pretty much the same result as you all had by the end of the workshop, with a small difference in the plotting is that we now have this white dots everywhere, or at some locations, and these white dots are the sensors, right? So we compute the pressures and fluxes with a given distribution of the permeability, which, as you can see, it's plotted in logarithmic scale, and it's 1 everywhere, so it's logarithm of k is 0, so it's 1 everywhere, and in this central barrier, it's 10 to the power of -6, so 6 order of magnitude lower. It's pretty much impermeable wall, impermeable barrier. And after we computed this forward problem, we remember the pressure, the values of the pressure at these locations, only at these locations. They don't even include the pressures inside this barrier. And then we are going to throw away everything. So all the knowledge about the forward problem, we will start from some distribution, some initial approximation for the permeability everywhere in the domain, which in our case will be just the uniform permeability, so the constant value of 1 everywhere in the domain. And we will try to, using only the knowledge of pressure at these discrete points in space, we will reconstruct it. So let's get to it. Yeah, it's kind of, it will be several small substeps. And the first substep would be to refactor a bit the codes that you already had by extracting the forward solve into separate functions, not the files functions, sort of that. Well, we unfortunately don't have really don't have much time. It would be really nice to do that for a bit longer, but we don't have that much time, so we did pretty much a lot of setup for you, and you will have to fill in the blanks as usual. You can start from the file geothermal_2d_ps_inf, and you will have some of the question marks. So if you open this file, you will see that it looks very similar to, at least the beginning, looks very similar to what you already had in the previous one. So we can compare. So these, that's the solution file for the previous thing, and the beginning is pretty much the same. We import also Enzyme and Optim.jl, which are the packages for automatic differentiation, of course, and well, optimization. But then it's very similar, and we have 2 extra functions, smooth, which will do the regularization for us. So I won't dive into detail, but the if we just try to invert, just to go along the steepest descent direction, yeah, or well, with any other approach, then it can generate really noisy distributions of permeability fields, and we have to regularize them. And there is the regularization, which is equivalent to smoothing, so that's the simplest one. That's why we have these extra functions in here. Then you have the same for kernels as you had before, so you can just simply copy and paste what you already did in the previous part, or you can just copy and paste it from the solution file if you don't have it yet. All right, so yeah, let's do it quickly. Okay, now we're back to the back on track, and now here the differences start a bit. So instead of doing everything in the kind of one main function, which is probably the simplest way of achieving this, but this is not very convenient because now we will have several solvers. So we have forward solver, we'll have a join solver, we have the objective function, and we will need to do it's in the loop, or well, actually we will need to pass the functions that define our objective function as gradients to the optimization package, and so that's not really convenient to have everything in one. main function, so we would need to refactor a little bit the solver. So we just extract everything that has to do with forward solver and put it into a separate function, which is conveniently called forward solve. And yeah, inside it does pretty much the same things as the forward solve in the previous vector. So it does some setup. We pass some parameters in the named tuples. In Julia, here we just unpack all these things and we do the same iterative loop. There is one kind of small difference, is that now we also pass the parameter which we want to optimize. And here you see it's not permeability, it's log k, it's a logarithm of permeability. And why we're doing this is because, well, as I said, the permeability in the subsurface actually changes usually in logarithmic scale. So it's not kind of absolute changes that matter, but the changes in orders of magnitudes. And if we optimize for a logarithm, the problem which will be much more kind of stable and robust. And on top of that, we're guaranteed to never have negative permeability, which is just unstable, and the solver solution will just blow up. We don't want that, so we optimize for a logarithm of permeability instead. So the rest is the same. So you can just copy and paste this main loop. You can just copy and paste this 4 standard updates. Yeah. So well, that was the boring part, which was just recovering the forward solver, and we can actually try to verify that we did everything correctly with the forward solver. So yeah, we can go then to the main function, ignoring all the rest. And then, well, we have some things, and but the important part, so where the differences with the previous file start is here. So when we define the visualization information, we do the same in the previous file, we define all those things, and then we go straight to the iterative loop in the previous file. And here, instead of that, we define this named tuples with all the fields that are required for the forward solution and for the visualization as well. And then instead of going to the iterative loop, we will need just to call a function with the forward solver. So yeah, let's do this just kind of by inspecting the signature of the function forward solve, and trying to figure out how to do this. Mhm. So, going to comments the rest if I want to really execute this. So, yeah. So here we see that really, if you did everything correctly, then we're back to where we started. So yeah, so now we call it the synthetic solve, because this would be the solver with this kind of synthetic pre-described distribution of permeability that we will want to invert in the following. All right, so now we have this. Now we can start slowly uncommenting the things. So now we need to store the true data. So the kind of, now we need to store the pressure at these locations. No, we need to store P, the regional pressure. And we did already, so we computed the indices of the of these locations in advance. So if you go to the pre-processing, there are this IX observe and IY observe, which are the specific, so the indices within the array, which corresponds to these locations with just the nearest neighbor search. So, oops. Okay, so by now we save this PF ops field, which is just kind of a scatter, so a tiny subset of the original data. So it's not even, it's like 8 by 8 points, right? Which is compared to the original resolution. So it's 127 for right times 255 for inwards. Yeah, this is not even 1%. This is 0.2% of the original data. So it's extremely small, smaller amounts of data that we save, and then we're going to forget about anything that we know about the synthetic solution. The next step would be to compute the adjoint solver, to do the adjoint solve. Right. For that, we introduced another function which is conveniently called adjoint solve, and it accepts similar arguments. So it also accepts logarithm of k, which is not used here, but when you look for consistency, it accepts the same parameters as are needed for the forward solver, because as I said, you can intuitively imagine the adjoint solve as like a tangent in the Taylor expansion of the original forward solve, with some transposes, but it doesn't change. So we need to know where do we evaluate our function, around which point. Then we pass some adjoint parameters which contain this extra fields, and on top of that the adjoint variables for which we need to run the pseudo-transient solver. And on top of that, some other things that we don't have time to really cover. But now, when we look at the iterative loop here, then it will become pretty obvious that it's very similar, extremely similar to the iterative loop for the forward problem, right? So here, while until convergence, we call this with this for kernels. We update residual fluxes, update fluxes themselves, we update residual pressure, and then we update the pressure itself using the residual. And here, well, first we do some initializations of this extra adjoint variables, or shadow variables on top of that. And then we still call the same for kernels. So we residual fluxes with derivatives. Then we call update pressures. We update, no, not the pressure, but adjoint pressure with this associated PF field. And then we call the residual pressure with differentiation, and then we update fluxes. So it looks a bit different. So the order of calls is different, it's really kind of, if you would imagine it as a 2x2 matrix, right, with fluxes, with residuals, fluxes, then this one, it's like, it's transposed, and it's also in the opposite direction. So we do the same steps, but with a transposition. So we compute residual fluxes, and then with the results of this residual fluxes update, we update pressure and not the fluxes. And the reason for that is because, as I said, the flow direction of the information in the reverse mode of accumulation in AutoDiff is reversed compared to the normal flow. So we don't start from the inputs and go to the outputs, we start somehow from the outputs and propagates the derivatives towards the inputs. So now we will have to populate this question marks. And well, the beginning is simple. The residual fluxes is yeah, the following signature is the same, but now here we need to figure out which variables do associate with what. And here the convention is very simple. So for each active input variable, we need to associate it with with the same variable but with a bar on top. So let's just do this.
Maybe while you're finishing to type, and also because I guess we really don't have much time left. So maybe just one thing to highlight is so really one of the cool things is that the adjoint solve, although we have to handle the way, well, how we map these extra storage or shadows, but if we look at the physics point of view, so we just reuse the kernel of the compute function from the forward solve. And most importantly, so the update functions, update flux, update pressure, they stay exactly the same. We don't even need to make AutoDiff on that. And it's really just these two residual functions or kernels that would need, well, first of all, they stay the same. So we don't have to think about typing in something else in the physics. But yeah, we just need to think how we call automatic differentiation on those. And it's really powerful because it means also the other way around. So if I have different physics, I can just change the physics in my physics kernel. I won't have to change anything in the adjoint solver automatic differentiation framework. And that's really important. Maybe you can kind of take a few more minutes to finalize this, such that I can just finish with the parallel, show the parallel implementation, because we just have like 10 minutes left.
Yeah. We're almost done. So this unfortunately this is a very short, or fortunately I don't know, but this is a very short exercise here. And so, yeah, thanks for the comments. So yeah, the important part is that if you change your forward physics, you just change your forward physics and you don't touch the rest. If you have introduced nonlinearities or whatever else, this will be the automatic differential will take care of the rest for you. Okay, so yeah, now as we just did this, now we have two more important things. So here we have two new functions, loss and gradient of loss. And to compute the loss function, which is, as we already saw, it's 0.5 times sum of pressure at our locations minus the this PF obs, so minus the observations. So that's exactly what we see in the README. And to compute this thing, we need first to compute the pressure, right? So we need a forward solve actually. So let's just do this. We just pass down all the parameters that we accept in this loss function. Nothing really crazy. And in the gradient of loss function, we need to do two steps, right? So we need first to compute the forward solve, and then to compute the kind of the tangent of the slopes, right, with the joint solve. So here we just need to joint solve. Yeah, so also nothing crazy. We just get inspired by the signature of the function, and finally we need to evaluate the gradient, right? And that's the most substantial part, because that's in the end what we need to do. And to know what to do here, we just need to look at the README, so which says that this gradients, when we know the adjoint solution, we just need to pass down the adjoint parameters and to feed them to the partial derivatives of the residuals with respect to the permeability field. So this is what we just need to do here. Let's slide x with a minus, right? So here you see minus q. We also have this part, drpf by dk, but our residual pressure doesn't depend explicitly on permeability, so we just don't have that. Y. And here, what we need to call is we need to differentiate the residual fluxes, right? So residual fluxes here, and we just pass here. Then we need to our so that would be the inputs, right? So we propagate these two vectors, and in the end we will store the results in the adjoint variable, so this shadow variable with respect to this k. K goes to this log. We actually need the derivative with respect to log k and not the k itself. But this is fine. So here, then we will take care of the conversion with manual application of chain rules. It's not a big deal. So yeah, that's the gradient loss, what we needed to do here. And now we're almost good to go. So now we have a synthetic solve. Now we can really uncomment pretty much everything here. So let's just quickly go through these things. So first we introduce two shortcuts, right? We say that's the j, which is our objective function. We now make it a function of only one argument, and then we just call our function loss, which contains the computation routine to really compute it. with all the params that we pass down here, and the same with number j, which is now just a function of 2 arguments. So the first is which we mutate, where we would store our log k and the value around which we do the expansion, and then we pass it all to the gradients of loss function. And then what we do is we start the inversion, we set up the initial guess. So we said the permeability everywhere is just a uniform function, is a uniform distribution without the barrier. So we forget everything that we know. We set the log k as the logarithm of k, of course. And then we can write the optimization routine ourselves, for example, with this gradient descent. But we will use the we don't have time for that, and it's nice to see that our approach is compatible with Julia ecosystem, and we will use the package that's called Optim.jl. You can read the documentation. It's simple, so everything boils down to this function optimize, right? Which accepts as a first argument the function that we want to minimize. As the second argument, it could accept the function that would compute the gradient, right? And it could be mutating, so we can do it in place, which is exactly what we did. Then we pass the initial condition, initial approximation, and then the methods that we want to use, right? And yeah, for the sake of saving time, I will just, you're free to figure it out yourselves, but I will just here, change, then class k, initial, S, and on top of that, we can also pass down optimization parameters, which I prepared for you. It just kind of stores some tolerances and the maximum number of iterations, so nothing really crazy, but I just did it. Okay, so now we can check. So yeah, these things, call it. And now, yeah, as you see, we computed first the forward solution. And then we see that something happens. And this is Optim.jl that computes the, well, this fancy LBFGS algorithm with kind of state-of-the-art line search to determine the step size. And then it's, well, yeah, it will just guarantee to reduce this discrepancy for you. And when it will finish the computations, we will extract. So we will take the minimizer of this optimization function, and we will, well, compute the exponents to convert it back to k, and then we will just plot the result and the convergence history. So this is what happens here. We extract the trace of the optimization and we just plot the results back. All right, so it will take some time. Actually, we're now it's the 5th iteration, and it takes around 8 iterations. But because we have line search, it actually does some internal. So the number of calls to the forward solution is around 100. But this is actually still much less, as if we would do this one forward solution for every grid point to compute the kind of the small perturbation around this point. So that's the beauty of this gradient-based adjoint methods. So yeah, that basically wraps it up. Thank you for listening and for following. And yeah, then I guess we could answer some questions, and yeah, then Ludovic could also briefly show what would it take to extend this to multi-GPU to make this code to scale to many thousands of GPUs potentially. So yeah, we're almost here. So we will also see some nice, well, some interesting property that's actually the minimizer of the function, wouldn't really bring us all the way through 6th order of magnitude drop in permeability. So it will actually compute a bit, well, smaller drop, which would be only, I don't know, 3 or so orders of magnitude, but this would be enough to already match the observations. And this is the limitation of this well, automatic inversion algorithms. They are not able to give you the ground truth. They are only able to do you any, so not the unique, but any solution that minimizes, that makes your discrepancy between observations model as small as possible. But yeah, in short, this is it. And as you can see, it's kind of all it takes to write as a joint solver is basically repeats the same iterative loop with minor modifications. What people sometimes do is that they try to use automatic differentiation on the forward iterative loop in the first place, and then it will give you the same result, and it will be even more automatic, so completely black box, no extra solvers. But if you have many iterations, then the adjoint, the AD, the enzyme will have to store all the intermediate results, and it quickly would blow up memory. So that trick allows us to replace it with just another iterative. So yeah, so that's the final solution. We can compare what we started from. So that's the synthetic solution. Is 0 everywhere, -6 in the center, and the inversion. So it reconstructs these low barriers. So it approximately kind of picks the location and actually drops it, not by 6 orders of magnitude, but by 2 something, so 2.5 orders of magnitude, and we reduce the objective function by 2.5 orders of magnitude as well. As we can see, the pressure field is well, essentially the same. It is a bit different around sources, but we actually don't have any information close to sources. So we only use the information from this kind of sensors, and but still we are able to kind of infer at least something. So yeah, that's it.
That's pretty cool. Thanks for the
that part. I guess because your time is a lot over, so I still will, but we can see how even that, but yeah, just people that want to stay like 5 minutes more in the room, I can just show
the last bit, which is like just the kind of multi-GPU code, because it's kind of what was promised somehow in the workshop. So yeah, so first of all, the same code that you showed that runs also on the GPU, and quite faster. And that's the nice thing with Enzyme, is that actually the function here that or the one that one can differentiate GPU kernels, and that would generate new GPU kernels that also execute on GPU. But yeah, maybe just the final word, which is like, if we take that same code, like that, the full inversion code, but now we add implicit global grid and MPI, which this is a package for distributed memory parallelization running on the CUDA, on GPU, then basically we don't need, so the nice thing is that we really don't need to change anything in the physics. So I still have my physics, and these physics, they are like somehow in that framework, in a, let's say, multi-GPU and distributed memory parallelization framework, they're really local to, they don't know about how the domain may be splitted on different GPUs, etc. It's just like my rules for a single grid point, and then I have to care about the rest in a different way. Now, really the nice thing is that, well, the way one would do it classically in the forward solve is that, well, I have some arrays which have this halo that I need to exchange to make my distributed stencil code to work. And this is what's done here. So my fluxes are the largest array. So I need to update the halo on the fluxes. So I would need to call this update halo, and I would call MPI boundary update on these processes. And here, one nice feature that I don't have time to explain, it even hides communication, which means like it will use the fact that it will compute the flux kernel first for the outer grid points of the local problem. As soon as they're done, I can make MPI exchange, and then while this is going, I can compute the inner points. And this is handled automatically between ParallelStencil, which has hide communication macro, and implicit global grid, and they work somehow together there. So that's very standard forward solve, how one would do it. Now the nice thing is that the joint solve, it's exactly the same thing. And importantly with that approach is we can really just replicate again. So here I have, well, my adjoint, my residual fluxes now called through enzyme. Well, I can just, well, I would just need to, well, call the update halo, sorry, on the fluxes on my adjoint fluxes. And just because I have boundary condition on pressure, I also need to update halo of adjoint pressure. But this, I could formulate the problem a bit differently and I would get rid of it. But so here you can forget about that MPI exchange. Really the nice thing is that it's like the forward solve. The adjoint solve has actually the communication of the adjoint fluxes, while for the forward solve we needed to care about MPI communication for the fluxes. And that's it. And even more importantly is that, well, somehow we don't call enzyme on a function that contains MPI communication. So somehow that's what I was saying at the beginning. With that approach, you have your AD part is really like at the most inner level. So it doesn't matter. Well, we don't need to, well, we don't imagine the mess if one has to call AD of something that is then piped to MPI that is distributed all around server. So that would lead to huge like latency and maybe not work. So that's really the nice thing. And that's actually the only changes. And with implicit global grid, this package, so the only thing, I have like 3 functions that I need. I need now to init my global grid to say like, well, what's my distributed memory topology? Then I have these update halo functions that are called in the forward and adjoint solver. And I have my, well, just finalized global grid, which is tear down MPI basically and free the buffers. And well, that's the only thing I added here, plus handling visualization, but that's kind of, that's nothing really big thing. And with those things, what I can do is I can now actually, so I'm on a server that has like, I don't know, so I have like this 8 GPU server, and well, I can just now actually use, well, call now my script, my Julia script, wrapped in MPI run. So that's the standard way to launch Julia with MPI. So MPI run, and then this, well, know how many processes. Here I want 4 MPI processes, and I attach, so implicit global grid would map 1 GPU with 1 MPI process. So I get my, basically my device ID, I get it from my local rank that maps the global rank. And yeah, I launch Julia and I launch that code. And so here I'll try to, what I try to do is I'll try to make, well, the same inversion that Ivan was showing, but now on CUDA, like on the GPU. And here the local problem size, well, I can put it to 255. So it's 255 by 512 on 1 GPU, and I do it on 4 GPUs. So it will be 512 by 1024 roughly. And yeah, and with the fully like GPU MPI thing, so I can try to launch this code here, and well, takes some time to launch Julia on MPI.
Basically, we are using Enzyme only for the inner function, right? We don't use Enzyme for the payload functions.
Yeah, exactly. So Enzyme is really just on the kind of the most inner part where we just want to get another computation of our residual. And I mean, that's really powerful because it's really, like this, we have full control because we know the thing we call enzyme on has no, well, it's really the most inner stencil operation that has no disturbance from the outer part. And then that makes things like, well, that you can easily just, so you don't call MPI inside the enzyme function, you call MPI around an enzyme function, and then actually the enzyme function or the execution of that, the kernels, the compute kernels, they, well, actually don't know about MPI because they would then they will be distributed on different GPUs or CPUs and just do the standard job, like not knowing that they're part of a bigger problem. So yeah, here it just would, so now it starts, so it would display that, well, I have like repeated 4 times, like in this weak scaling fashion, my local problems. So I have like 1000 by 1020 by 500 because I have some overlap on 4 processes with the given topology, and then ideally it will just run on 4 GPUs and do my inversion in a parallel fashion. And maybe for while it still kind of starts. So the only thing I had to change, so well, now you can see, so it does the same thing. First, the synthetic, that's done here. And then it would start the, well, inversion procedure. And now the kind of only difference is that here I don't use Optim with this LBFGS, because this LBFGS uses internally some dot products, which would obviously not work out of the box, because now I have my arrays are distributed on the whole server. So I need to, well, either I would need to go in Optim and fix and make some parallel support there. But now for that purpose, I just instead program myself. So what's going on here? It's just like, vanilla-like gradient descent that's here. So it's also in the README of the GitHub. So you can see, so it's kind of just, I now manually call the gradient of the loss function to get back this dj by dk, log k, my parameter. Then I can define a step size, and I can here make the, well, update. So I have the gradient dj d log k times the step gamma, and I update log k, and that's it. And then I just evaluate the cost function for monitoring the thing, and I repeat, and all the rest, that's all plotting. So that's just my gradient descent, now calling basically these 2 functions, grad j and j. That's what I was piping through Optim, but I can just use it for my own purpose with making another type of gradient-based inversion here, just simplest gradient descent. But yeah, I don't need any global operation in that approach, and that's why, well, now you see it will, so now that's kind of what it does. Well, it will do, I guess, 50 steps to make 1,000, basically, on the 1,000 square grid point level inversion. Now, 50 gradient descent steps in kind of, well, maybe a couple of 1 or 2 minutes on 4 GPUs. And, well, I ran it this morning, so, and that's, so with gradient descent, that's what we would get. So it's pretty much like, this here. So, well, same story as before. It was even showing, now it's like, well, 1,000 by 500. It's kind of decomposed, like if I would color by rank, I would get like 4, like a 2 by 2 tiles of different GPUs. There's no artifact, so communication across process works well. And yeah, well, that's now the convergence, not of this LBFGS, but of just simple gradient descent. But I also lose 2.5 order of magnitude over like a couple of more iteration, but yeah, there are no inner calls hidden or whatever. So all in all, it works fine. And the reason, as Ivan also highlighted, so the reason here we don't recover 6 order of magnitude impermeability, it just means that basically that's enough to make it feel like impermeable. So yeah, and that's kind of also a nice thing. So that goes more in the direction what seismologists call this sensitivity. So you can see how sensitive your problem is to a given parameter. And here it just means that, well, actually, if I would run the same code, the forward problem, just with 3 order of magnitude in the reduction in my permeability barrier, I would get the same results, basically. And all what I add more, it just makes it stiffer, but not really kind of significantly changing my results. And yeah, so, well, I guess the codes are there. So the parallel code, it's even just it's no question mark. So you can just take it and run it on whatever server that has multiple GPUs if you want to try it out. And I guess, yeah, well, so that was a bit the last part here. And you can read more about also implicit global grid if you're interested. That implicit global grid is just like distributed memory parization. Doesn't need to work with ParallelStencil and doesn't need to work on GPU, but they combine nicely. And yeah, well, I guess for the few of the ones who remain, well, thanks for staying until the end. And yeah, I hope that, well, at least one of the other bit was interesting and useful. Yeah.
When you try and follow this course methods of stencils, and the way they manifest was unhelpful stack trace. What's the procedure to see how the macros expanded in debug and get a more useful stack trace out of those?
Yeah, that's a good point. So I don't know, Sam, do you have any recommendation how you could debug?
When you debug stencils, when you make a typo in a stencil, run it, you get a very unhelpful stack trace. Unfortunately, in my case, it was an obvious typo, so I found it. When it's less obvious, what's the sort of debugging procedure for going through and seeing how you made a mistake in a stencil?
Well, first of all, you run on the CPU. Did you do that?
I didn't try that, no.
Okay. The thing you run it on the CPU, as with all CPU programming, it's very complicated. So if you just go to thread, you run on thread, and then you can run on a single thread, and do usual debugging like during container.
Okay.
Yeah,
so
technically should develop everything in CPU only, and once it works, only then you run in CPU.
So the thread does. I didn't try running with threads. I just tried running. So that gives better stack traces. Thank you.
Yeah, well, so here it will. This is also done now, so that's like the last iteration step, and then will have produced the new figure, which is the same as the previous one, obviously. And yeah, well, so that's mostly it. So yeah, and well, just since it's here, some nice things. So we see that in the broader scope of the inversion procedure, so the first call to the forward solve is just to evaluate the loss function. And then actually the adjoint solve, it's a bit heavier solve because, well, the kernel passes through enzyme, and one has to, well, make this, well, automatic differentiate the call. So that it's kind of, well, it's not shown here, but kind of it's a bit like there's a kind of 30% overhead because it goes through the enzyme, but which is not a huge thing. It's kind of enzyme managed to generate a quite efficient kernel automatically that only runs at 70% of the forward kernel while doing all the accumulation. Since the adjoint solve is linear, it needs much less iteration. So one needs actually fewer iteration on a bit heavier solve, and then like the forward solve, which is also pretty fast. So all in all, it's kind of pretty efficient iterative things.